Hello, this is our EECS 203 project, Proof by Contradiction, by Kumar, Thomas, Aaron, Jesse, Matthew, and Horace. Enjoy! Now, before we explain what proof by contradiction is, we have to explain what contradiction itself is. Now, a contradiction is a proposition that is always false. That means it's two or more statements that negate each other. For example, the statement P and not P. Now, P and not P have opposite truth values. That means when P is true, not P is false. And when P is false, not P is true. So if you plug in these truth values into the statement P and not P, P and not P will always evaluate to false, making it a contradiction. Now, let's explain this in a more broader sense. Let's make P the statement, everyone is happy. And we'll make not P the statement, no one is happy. Now, P and not P is a contradiction because it's impossible for everyone to be happy and no one to be happy at the same time. This is a contradiction.
Arthur Conan Doyle said, "When you have eliminated the impossible, whatever remains, however improbable, must be the truth." The concept of a proof by contradiction is, by using a proposition's negation, we can show the validity of that proposition. A more in-depth explanation states that because the statement Q and not Q is a contradiction whenever Q is a proposition, we can prove that P is true if we can show that not P implies Q and not Q is true for some proposition Q. This type of proof is called a proof by contradiction.
For our first example of a proof by contradiction, we're going to try to prove that there are an infinite number of primes. So we'll begin by stating our proposition. So our proposition P, there are infinite primes. With infinite primes. So to begin, I'm going to state our negated proposition, not P, which will be that there are finite primes. So it is known through other proofs in mathematics that the product of a sum of consecutive numbers plus 1 will be relatively prime to all numbers in that list. So we can apply that to, you take the factorial of a number n and add 1, the result is relatively prime with all numbers 1 to n. So if we are assuming that there are finite primes, then that means we have a largest prime. Let's call this largest prime P1. So we are capable of taking the factorial of P1 and adding 1 to it, just like we would with any other number. I've just stated that the factorial of a number plus 1 will equal a prime number. However, the factorial of a prime number, or any number, plus 1 will yield a larger number than the number we began with. So if we say our prime number P2, let's call this P2, will be larger than P1. Therefore, if we look at our negated proposition, we're implying something and its negation. So for example, we are implying, let's say Q, that there is a largest prime, and not Q, since we have just shown that we have found a prime larger than what we believe to be our largest prime. Since Q and not Q will always yield false, not P must then be false. Since not P is false, we know P must be true, and therefore, from proof by contradiction, we have proved that there are an infinite number of primes.
A proof by contradiction we'll prove that the square root of 2 is irrational. So to begin a proof by contradiction, we start by defining our proposition P, which is that the square root of 2 is irrational, and then stating the negation of that, not P, which is that the square root of 2 is rational. Now, to define rational, we say that there exists two integers, a and b, which are elements of positive integers, such that b is not equal to 0, and that a over b is a rational number, which means that a and b are in lowest terms. So since we're saying that the square root of 2 is rational, we can rewrite this as square root of 2 is equivalent to a over b. Now this is equivalent to 2 equals a squared over b squared, or 2b squared equals a squared. Now from here we know that a squared is even, because any integer squared and then multiplied by 2 will be an even number. So now we know a squared is even, and because the square root of an even number is also an even number, we know now that a is even. Okay, so now from here, we can say that since a is even, it is equivalent to 2c, where c is any integer, because any integer multiplied by 2 will be an even number. So this original statement can be rewritten as 2b squared is equivalent to 2c squared, or 4c squared. Now this can be simplified by dividing by 2, so we get b squared equals 2c squared. And now from here we can see that since b squared is equivalent to some integer squared multiplied by 2, we know that b squared is even. So now we see that b squared is even, and thus, as we proved before, b is also even. So now the original statement, not P, which says that square root of 2 is rational, or that square root of 2, which is equal to a over b, is in lowest terms, since a over b, will be rational when a over b is in lowest terms. But yet we get this statement here that says that both a and b are even, or that a and b can both be divided by 2. This is a contradiction with saying that a and b are in lowest terms, because a and b cannot both be divisible by 2 and not divisible by anything. So now we have a contradiction which says that not P. So we had the original statement that said not P implies, say, a and not a, where a is that a and b are in lowest terms, and not a is that they're not in lowest terms. So now we know this is clearly false, because a and not a is false, and not P must be false, because it's a contradiction. So now we know, since not P is false, P must be true. And so now we've shown, through proof by contradiction, that P must be true.
This has been our presentation of proof by contradiction, and I hope you enjoyed it. Thanks for watching.